Welcome to the fourth lecture of the Geodesy track in Advanced Techniques for Mobile Sensing and Robotics. We are now here at the fourth lecture, as I said, and what we've talked about so far was that in the first lecture we generally talked about laser scanning, mobile laser scanning, and I explained the georeferencing equation which holds for a laser scanner which is moved through the environment either on a car or maybe on a UAV or something in order to generate globally referenced points and the transformation that needs to be done. In the second lecture I repeated how these trajectory parameters here are generated. So this was more or less a repetition of what has been done the first semester, but also some add-ons like smoothing. So how can we generate roll, pitch, yaw, and the 3 coordinates of the mobile sensor system that is moving through the environment. The third lecture was on system calibration, so how to get those 6 parameters here, which describe how the actual mapping sensor, in this example a laser scanner, is oriented on the body platform. It's important to know those because usually we get the trajectory parameters as parameters of the platform in the global system. And we of course need to know how the scanner is oriented and placed within the platform. The same holds for cameras, like in this example here for the plane, where the camera here, it's the same thing. We need to know where the camera is on the platform and how it is oriented. We focused on laser scanning and also looked in a bit more detail on how this is done using a plane-based calibration procedure. I already said there are few different data rates on sensors. I just want to give some examples here, just to give you an overview what different data rates means. So we have a GNSS receiver is usually giving you something between 1 and 10 hertz. Some receivers give you even more, like 20 hertz, but usually this is a bit artificially high based on internal algorithms of the receiver. I wouldn't expect more than really 10 hertz from a GNSS receiver. Usually that's also more than enough. Inertial measurements usually mostly give you 100 hertz data. High quality ones, expensive ones can give you even 1000 hertz. And here's also the question, if you really need that. That depends probably mostly on how your dynamic actually is, how fast you move and how fast your rotations and everything are. Laser scanners have a point rate of up to 1 megahertz or even more. And if you talk about profile scanners, this can be done with profile rates of up to 100 or 200 hertz. So that means that there is 100 hertz profile rate. I have 100 rotations, full rotations per second. Cameras usually give you something between 1 and 100 hertz, so you can have like fast video cameras, but also potentially more higher resolved, higher megapixel images with lower data rates. And depth cameras like IntelRealSense or something like this give you similar data rates. Okay, and this is of course a problem because it's not only the different rates, it's also that there may be offset between the clocks, right, of the distant sensors. Okay, if we want to understand and see why this sensor synchronization is so important, we can have a look at the georeferencing equation here. So in this equation, we assume that the transformations here from the calibration and from the trajectory estimation are valid exactly at the same time as the sensor measurement, the scanner measurement is done, right? So there's a distance measurement and an angle measurement in the scanner, and we need to have at exactly those times points in time where these measurements are done, we need to have those calibration transformation and the transformation from the parameters, from the trajectory. This is very important, and we assume these calibration parameters usually to be constant and changing over, not so much over time, but these are of course changing because we're moving, right? Then if these are now known at time t1 and these scanner measurements are known at time t2, and there is a difference between t1 and t2, let's call it dt here, then this, of course, this dt, if it's unequal to 0, leads to wrong assignment of observation to the trajectory and therefore to a wrong transformation in the georeferencing equation, right? So this directly transforms to a wrong, to an error here in this point. And this error depends, obviously, on the moving speed and the rotation rate of the vehicle. We can see this here in this graph. This graph shows the translation error due to time sync error. So we have here two lines, and one is representing moving speed, which is similar to walking speed, like 1 meters per second, and the other one is 50 kilometers per hour, which is roughly a car in an urban area, let's say. And here we can see what the relation between a time synchronization error to a translation error is, right? So that means if I have millisecond, like 10 milliseconds synchronization error, this leads to about 14 centimeters position error in my georeferencing equation. Yeah. And if we now say, okay, with respect to translation, we want to be not worse than a centimeter. If this is our accuracy goal of the whole system, right? Then we have to say, okay, 1 millisecond is the necessary synchronization that we have. So it shouldn't be more than that. Otherwise, we're not below our goal of a centimeter, let's say. Okay, this is just to give you an idea what time synchronization numbers we're talking about here. You can, of course, because it depends on the velocity, you can plot this in a different way. You can say, okay, what is the required time resolution in milliseconds in order to get a certain spatial resolution? And if we go to, like, let's say the half of the 50 kilometers per hour, that was from the last slide, right? So that would be here, if we need 1 centimeter, we need 0.36 milliseconds here, or yeah, if it's only 50 kilometers, it's double this. So it's just below a millisecond, right? So this is what we need. Okay, and if we even want to have more accuracy, like a millimeter, then it needs to be way below a millisecond timing synchronization error. This just, yeah, this makes clear that it depends on the speed of how you move, of course. You could also look like the synchronization if we stick to the could look at the orientation. So if we stick to the example from the mobile laser scanning, and we say, okay, we have a car which drives here around that corner, and we say, okay, the rotation rate in that corner is roughly 90 degrees per second, so it needs 1 second to do the actual rotation around 90 degrees. It's just a rough estimation. I don't know really if that's precise, but it should be roughly okay. Then you can say, okay, this 1 millisecond, then a millisecond of timing error leads to an angle error of 0.1 degrees. Yeah, and if we assume a distance to the car for the scanner measurements of about 10 meters, yeah, then this 0.1 degrees of angle error transfers to a 1.5 centimeter position error. This is for 10 centimeters. It is of course lower if you're closer to the vehicle, and it's even more if you go further away from the vehicle. So here also you can say, if you assume I go to the city and everything which I'm interested in is not further away than 10 meters from my car, then you could say, okay, these 1.5 centimeter accuracy requirements lead to these 1 millisecond that we have seen before, right? So I would conclude that if you want to use a mobile mapping system in a city, for example, to accurately generate maps with a accuracy in the order of a centimeter, then all sensor synchronization should be better than a millisecond. There's another important thing where synchronization is important, and this is, of course, I mean, so far we talked about measuring, right, acquiring perception of the environment. We just haven't done anything. But if you want to do something at a specific position, right, if you want to manipulate the environment, you have control loops, want to perform an action, then of course it is also very important that your synchronization between your sensing and your actually your action is well done. There is this example here of GNSS controlled sugar beet seeding. This was a project that we did years ago. I will come to that later. But here the plan was based on the GNSS coordinate to place the sugar beet very well controlled with a very known distance to some line at the border of the field, right? So it was necessary to place a sugar beet using this wheel here, a sugar beet seed at a certain position on the field. And of course, if you want to do that, you need a very, very good synchronized system to do it. Otherwise, everything will be kind of delayed. Yeah. Okay, so the same holds, of course, if you want to do spraying, if you want to go to the field and want to do something at an absolute position in the field, like spraying a specific plant where you know the coordinate from, or something like this, then you of course need a good time synchronization of all components which are involved in the process. Okay, so what is the problem with synchronization? So why is it difficult? I basically say that there are three main problems with synchronization, yeah, that you have to solve if you properly want to do that. Yeah. So the first problem is how to assign a timestamp to a measurement. Yeah. Okay. So the question is if a camera makes an image, or if the scanner does the distance measurement, or whatever, right? Then the difficult task is to know exactly when this measurement happened, right? So assume we have a perfect time clock, right? But how do we assign the measurement of a sensor to the clock, right? So how do we know at what exact point in time the measurement actually happened? And this is one thing that you have to care for, and you have to look at it. We will see later how this is done in some example sensors. The second problem is what clock to use for timestamping. Yeah, so we have, like, PCs have clocks. There are different clocks everywhere around. Some are good, some are bad, and some are drifting, some are not so much drifting. So the question is, what is a good clock, and what clock can we use for timestamping? And are there potentially reference systems for time, so that if we say a certain clock, then everyone knows exactly what time that really was. And the third problem is if you have multiple clocks in one system, like a multi-PC or a sensor network, how to synchronize multiple clocks. So that's a third system. So I would say we have three things, like when is a measurement actually happened, so how to assign the timestamp to the measurement, what is a good clock in general to use for timestamping, and how to synchronize multiple clocks if you have multiple clocks or operating systems in your system. this summarizes what I said a little bit. So this might be a very well-known situation. So you have some sort of PC. This thing here now represents a PC or a laptop or a Raspberry Pi or some sort of microcontroller. So this is just some PC which is actually collecting the sensor data. Yeah, and it might be that you have one of these PCs and all the sensors are somehow connected to that single PC, which is collecting all the sensor data. So this is, although it looks like a very simple solution, simple problem, because you don't need to care for multiple clocks on multiple PCs and how to synchronize them. It's still the problem one here is still valid for each of those sensors, right? So when is the measurement actually happened? And this is what we can see here. There's another situation where potentially each of your sensors is connected to its own PC, or not necessarily PC, but maybe a microprocessor, maybe also a microprocessor which is within the sensor, whatever. But each of the sensors has its own PC connected. Then of course we have the same problem one here, right? But then we also have some more problems like problem 2 and 3. So how to synchronize these multiple PCs now and to make sure that they're all talking in the same, or they're all ticking with the same clock. Yeah? And what is a good clock? So this is problem 2 and 3. And the most realistic situation is probably like this, where we have one PC or computing unit which potentially is connected to, well, let's say like a stereo camera pair and a laser scanner. Then there's another one for the scanner, and there's maybe one which is connected to the IMU, so this is the inertial measurement unit, and some GNSS device. So this is a very realistic thing. So then we have again both problems: when is the sensors when is the measurements happening, and how do we synchronize those different PCs? Okay, we can go a little bit through some examples how these problems are solved. So we have problem 1, how to assign a timestamp to a measurement, and there are basically 3 options for that. And I will show examples for all of these options next. So option 1 is the sensor already provides you with properly time tag measurements, right? So you don't need to care because the sensor gives you its measurement with some internal clock which is already valid, which you don't need to get a pulse or something. You just get a time-stamped measurement already, and then you can go directly to problem 2, right? So what is the time base of that measurement and how to synchronize it with others? But then it's pretty good because you already have a time tag at your measurement. Option 2 is the sensor provides an electronic signal, like a pulse or something, at the moment when the measurement happens. So that's option 2, right? And option 3, the sensor performs the measurement at the moment it receives a trigger in form of an electronic signal, like a pulse. So option 2 was it measures and gives you information about when that happens by a pulse, for example. Option 3 is you tell the sensor when it has to measure. So that means that you create a pulse at a time when you know what the timestamp is, and then you tell the sensor to do the measurement at exactly that time, right? So that would be option 3. So option 1, like the stamped data, so this thing where you already have a stamped data, an example here is our GNSS receivers. GNSS receivers always provide data which are properly time-stamped in coordinated universal time, right? So each GNSS receiver gives you a position and whatever it gives you else, but it always relates that information to a timestamp in coordinated universal time, which is a global time reference, which we will talk about later, right? But they are already properly tagged. And most inertial measurements systems which contain a GNSS receiver, right? So like a box like this, where there's a GNSS receiver in there and an IMU with accelerometer, gyroscope and everything, they already provide data or also timestamped in UTC. So this is because they have internally a GNSS receiver, so their whole internal system is synchronized with this UTC, with a clock from GNSS. And then all the data coming out from here, like orientation, acceleration, velocity, angular rate, and so on, they're already timestamped. So this is option 1. We have properly timestamped values. Option 2 is to receive a pulse when the measurement is actually performed. And this is something where we can give the GNSS receiver as well as an example, because higher grade GNSS receivers provide an electronic signal at the time a GNSS measurement is performed. This signal is usually called PPS, like pulse per second, yeah, and it gives you a signal, an electronic pulse, exactly at the time the GNSS measurements are valid. Yeah, so this it comes in addition to the fact that all the measurements are already assigned to a proper timestamp. Yeah, and this PPS, the pulse per second, can also be used to synchronize other clocks, and we will talk about that later again. Right. So option 2, receive a pulse, is also the GNSS receiver as an example. Another example for receive a pulse are industry cameras. Usually industry cameras provides a trigger output which is synchronized with a shutter, right? So there's, just to give you an example here of this plot, so there is an exposure time, and when the exposure is finished, it gives you a pulse, right? And then you know exactly, then there's a very, very good synchronization between the actual exposure and this signal here, and then a device which receives this signal knows exactly when the measurement has happened. Of course, you have to care, you know, the exposure time, right? This here can be also a millisecond, right? Or it can be less than a millisecond. Then the question is, when is the actual exposure time? Is it the middle of it, the start, or the end? So if you want to be very, very accurate, you have to care for this as well. But anyway, there's a very strong and hard correlation between the exposure and this trigger signal. If you don't have an industry camera, but like an industry standard camera, there are also some consumer cameras which can be used similar, right? So here the option to receive a pulse is to put something on the hot shoe. So this here is for flash synchronization, and it usually it initiates or triggers the flash, and the flash is planned to be synchronous with the actual exposure, and then you can pick up the signal here, which is actually meant for the flash, and use it for time synchronization. Yeah. So this is similar to what you get from the industry camera, but it's just getting the hot shoe, and this is also what is most of the time done if these type of cameras are used in UAV systems to do aerial imaging. This is not possible with all cameras, and another problem is, at least we had the experience with that if you put something here, the camera may think that a flash is connected, and then there are some restrictions on the actual exposure time. So this can also happen. So it's not something which works very well for all cameras, but it's a possibility which is used very often. Laser scanners, we still in option 2 receive a pulse when the measurement happens, right? Most laser scanners actually provide a signal when the profile crosses 0 degree, right? So this is the example here of the profile laser scanner that we use in our mobile mapping system, and also this Hukoyu scanner, which is well known in robotics, and the Velodyne scanners. They provide you some signal when the scanner is so it's measuring around, right? So it does like 100 or 200 times per second. It does a full circle, and every time it goes through 0, it creates a pulse, and this pulse then can be used by some measurement system to synchronize, to know when the measurement actually happened, or at least the measurement at this year happened, and it usually no problem to interpolate these times then to all the other measurements in that profile, because you can assume that the rotation speed is pretty constant. So you know the time here, and for the next profile, you know this time, and then you can interpolate between here all the whatever 100,000 measurements which have been here, and then you can assign a timestamp to each of those distance measurements that are taken here, right? So this is then here, for example. Okay, and this works well with laser scanners. Now we're at option 3. The option 3 is send something to the sensor, and then the sensor does the measurement at the time when you decide. And this is more or less possible with some laser scanners, where you can synchronize the rotation speed of the internal mirror, the rotating mirror, with an external oscillation. Yeah. However, this doesn't really help in synchronization of in assigning a certain timestamp, because of course you can't say measure now, measure now, measure now, because it's a rotation oscillation in here. But at least what you can do, you can synchronize multiple sensors, multiple of those laser scanners to run at least synchronous to each other in terms of the internal mirror, right? So this is not really helping a lot in time synchronization. But yeah, I want to mention it here because it's basically an option 3 example for laser scanners. More often, this option 3 is used with cameras. So industry cameras usually provide this possibility. So you tell the sensor actually when it measures. So you give a hardware a pulse to the sensor, and then it does the measurement exactly at that time. Yeah, and this even sometimes works with there are camera protocols like GigE-Vision or something, where you can trigger these even with Ethernet signals to a very high accuracy. But the idea is, I tell the sensor when to measure, and this is how I assign a timestamp to the measurement. Some consumer cameras provide this option, but not all of them. There is one potential problem with this. You have to make sure that some cameras do some things before they do the actual exposure, right? They do some autofocus and brightness adjustment and everything. And of course, you have to make sure that this is not happening between the trigger and the actual exposure, because, or at least if it happens, you know how long it takes. Otherwise, you lose synchronization. If it does some autofocus every time, and this autofocus needs some time, and this time is different every time you do it, then of course it doesn't help at all, right? Then you lose synchronization after this. A last thing I want to show, which I call no option, is to use USB connected devices. I mean, of course, many sensors are USB connected, but what I want to say is that you can't really expect any proper time synchronization in this case. I just found an example to here, like I found a publication by some people who analyzed the latency of USB connected input devices. And in this example, this was a mice. And what they did, they analyzed the latency between the button click of a computer mouse and the actual reaction in some application where this button click is used. Yeah. And of course, this is a bit different for cameras. And I would think that in cameras, for example, it's even worse because there are much more data have to be transferred, and it's much more relies on how busy the PC is with other things. But there are different layers in the PC between the actual button click on the mouse, which is this here, then the microcontroller on the mouse, which is providing it, pushing it to the USB of the PC. This is here, and then there's the operating system dealing with these USB stack things, and then this goes up to the app, right? And there are many different stages involved between something which is outside of the PC and the actual application in the PC which does something. And this is here the so-called latency. And this latency is always different. Yeah. And this is the main problem. So this latency, the different latency is called jitter, right? So here in these examples, you see that for one particular mouse, which is this one here, like a laser game mouse, whatever, the latency was always something between this and this, right? This is just showing how often happened what. And what you see is, what the important point is, it's varying a lot, right? It's not just a latency which is always constant, it's changing, yeah? And the change here is in the order of 10 to 15 milliseconds, and the initial latency is already 15 milliseconds. So this is, as I said, just an example of a mouse, but it shows what's happening. So there's no way to do anything below a millisecond here with this computer mouse, and of course not with anything else which is connected to USB. These yellow things here are examples where the internal USB polling rate in the operating system has been set to a higher value. So then some things are a bit faster apparently, but again, this just shows that it's not deterministic at all, right? It gives you an area of when the relation between when you receive something from USB and when it actually happened or was sent, when the image was taken, is unknown in the order of tens of milliseconds. Okay, what is problem 2? Problem 2 is what clock to use for timestamping. Yeah. So if we say, okay, I know now how I get a grip on my actually moment of the measurement using a signal or something, what clock is a good clock to use, and are there any time standards which can be used? Yeah. And I want to just go through some general things on different time systems. And the general idea of measuring time is based on the observations of a periodic process and counting the periods, right? So how do you measure time? You look at something which happens over and over again, yeah, which is a periodic process like an oscillation, and then counting the periods. This is what we usually do when we measure time. And there are different periodic processes where we can look at in order to define our time. Yeah. And one process we can look at is Earth's rotation, yeah, which is pretty often used because it's very natural for us. It has to do with day and night and all these kind of things, right? So the Earth rotation is some process which we like very much because it reflects our day-to-day life. Yeah. Then the Earth's revolution around the sun, of course, is also a possibility. We will not talk about this now. And a third one, which is often used to define time, and this is actually also the official definition of a second is based on this, right, is atomic oscillations. Yeah. And I will give some examples about that now, focusing on universal time, because this is basically the thing which makes it good for us, useful for us, and the coordinated universal time, because this also includes some official definitions of the second, which is based on atomic oscillations. So there are different time systems, and there are much more, but I just try to list a few which are good to know about, right? So these ones are some which you always see, and which are which you not always, but which are the most relevant, let's say, if you talk about different times. Yeah. And one is the universal time, which is based on the Earth's rotation. So it uses the rotation of the Earth around its axis to define a time, and there are different versions of it, which account for changing effects, such polar motion and changing rotation rates, right? So the Earth rotates around its axis, but not always the same. So this rotation rate is changing over time. It's not constantly changing, it's even varying. And so there are many, many things which you can account for when you look at this time. And it's a very complicated thing to derive this, but there are people who do that. And they always update this universal time, and there are different versions of it, like the UT1, for example. This is universal time 1, which accounts for polar motion and changing rotation rates. Then on the other hand, there's the atomic time, which is based on the duration of a state transition of the cesium-133 atom, right? So I don't go into details here, but there's a possibility to count some specific energy state change in this atom, and count them, and then define that how long a second is, right? And the atomic time is basically adding up seconds. So there was one time in the past where it was 0, and then what it does, it just adds up one atomic defined second after the other, right? And this is atomic time. Unfortunately, because atomic time is very accurate with respect to how much a second is, it doesn't fit well to this universal time, which is always changing. Days are shorter, hours are shorter, and so on. And that doesn't fit well together. And this is basically handled by introducing the coordinated UT, which is a coordinated universal time, which is called UTC, right? And it's using atomic time seconds. Yeah, so it's using the very well officially designed length of a second, but keeping a maximum distance to UT1, to that time that fits much better to our actual feeling of the time with respect to days and nights, right? So it's always kept, so this UTC is always kept below 1.9 seconds difference to that UT1, which I mentioned here, right? And what this means is that I need to introduce leap seconds. So once in a while, I need to add an extra second, so that the UT and the TAI, so the atomic time and the universal time, somehow fit together. So every few years, a minute doesn't take 60 seconds; it takes 61 seconds, and this is what happens in the coordinated UTC. Yeah, but this coordinated UTC here is the time, right? So this is a time that is very absolute and very internationally standardized. So this is a time which is good to have. Yeah. So this is a coordinated universal time. Unix time is also, of course, something that people, when they program, use a lot, right? It's a number of seconds since UTC 1st of January 1970. So this is based on UTC, right? But it ignores leap seconds. So it uses seconds from the TAI, started at UTC here, and then counting seconds since that point in time, right? So there is an equation how to get UTC from Unix time and vice versa. And then there's something else which is called GPS time, and this is the time of the GPS satellites. It's not, to be honest, it's not so important to know about GPS time, because anyway, GPS receivers gives you UTC at the end, right? So they transform internally their GPS time to UTC. A receiver gives you UTC, usually not GPS time. But it's maybe interesting to know that they also maintain their own clock, but it's just an offset between this GPS time and UTC. It's just 18 seconds currently, but it changes depending on how many leap seconds we have introduced. Okay, this is just showing the leap second thing. So the UT1 here is going since 1972. It's changing like this, and in order to be always close to that UT1, the coordinated UT introduces those leap seconds here, right? So this is the introduction. So 1st of January 2006, there was an introduction of 1 leap second here. So this is now UTC, and every time when this distance here is too big, right, then another leap second is introduced. And okay, back to GPS. I already mentioned that GNSS receivers give you a proper time. They give their measurements in UTC, and I already said that they also provide this so-called pulse per second. The receivers provide the pulse per second. I just want to quickly explain why this is. In GNSS, as you may remember, we have those satellites flying around the Earth, and they're constantly transmitting signals, and these signals contain information about where the satellite is, right? This is those coordinates here, where the satellite is, and what time it is, right? And then these signals are received at some receiver here on the Earth, and the receiver tries to derive its own position based on the position of the satellites and the flying time of the signal between the satellite and the receiver. And if the receiver's clock in the receiver would be synchronized exactly, would have the same time, would be synchronized with the clock on the satellites, then you would simply use 3 satellites and solve an equation system with 3 unknowns, like the position x, y, and z, and 3 observations, which are this, and this, to solve for that position, right? But unfortunately, the time of the receiver, the internal clock, is drifting so much with respect to the satellite clocks that you have to estimate the offset of the receiver clock to the satellite clock every time you measure a position, right? And this at the end means that when I solve a position with a set of observations with my receiver, right? Then I solve to get three parameters, which are x, y, z, and the b. And the b is a receiver clock bias, right? So every time, and every time means probably 10 times per second, I receive my distance measurements. Actually, it's not a distance measurement. It's called pseudo range because it's still a distance, but with some unknown component due to the clock bias, right? This is why it's called pseudo range and not range, because it's not really a range. There's still some clock offset in there, which is unknown. I receive 4 pseudo ranges, and then I solve this system of 4 unknowns with 4 satellite observations to generate x, y, to estimate x, y, z, and b, right? And this is what I do. Usually, standard thing, every GNSS receiver needs to do this in order to get the position right. It needs to get the receiver clock bias right. And on the other hand, it means that I always have a very precise estimation of my receiver clock bias with respect to the satellites. So that means my receiver, my GNSS receiver, as soon as it has a proper position, it also has the best clock I can get, at least around, right? So all of my GNSS receiver are, when they have a position fix, when they have the position determined, they also know the time very well. This is summarized here. So a GNSS receiver which has a position fix has also a time fix, right? So it's not only position, it's also time. And this is because the bias between the receiver clock and the GPS time standard is freshly estimated every time it needs to do a new position, which is about 10 Hertz, right? And this internal clock of the receiver is then, of course, updated with this bias. So this internal clock then is perfectly accurate according to the GPS atomic clock or GPS time of the satellite signals. And if it's a good receiver, right? If it's not all receivers, the cheap ones usually do not do that. But if it's a good receiver, it also feeds this internal clock out in form of an electronic signal, and this is then called the PPS, the pulse per second. So a good GPS receiver always provides you, there's one pin somewhere which gives you a pulse every second, and this second, according to the time of the satellite GPS system, and so according to the universal controlled time. This information then, this signal, and also the time that you get from the receiver can then be used to timestamp sensor data or to synchronize other clocks, right? So this gives us a very good time reference. So every GNSS receiver is a really good time reference, which is stable within nanoseconds, right? So if you have this PPS, it is nanosecond accurate. You can see that here, this was a measurement that we did in our lab just for fun to test. So we have two independent GNSS receivers, right? And they're providing a PPS pulse, as I just described. And these pulses are both feed to this oscilloscope here. So the green one is receiver 1 and the blue one is receiver 2, right? And this here is a PPS pulse, right? So what you can see here is they're perfectly on time, right? So this here is microseconds. Yeah, so this is 50 microseconds. So this is probably 10 microseconds roughly, right? This is, you can't see a distance at all. This is way below a microsecond, how these here are synchronized, right? And then if you then have one receiver without a fix, right? So if, for example, you unscrew the antenna of one receiver, then this was here, the green one was, the antenna was removed, right? The receiver was still running. Then you can see that this internal clocks of the receiver drifts, right? So this is after 5 minutes, it's about 10 microseconds drifted, and after 30 minutes, it's roughly 50 microseconds away. And this is actually still pretty good. I mean, the receiver internally has still a good clock, right? But it's drifting. And if you have a PPS, again, then this would go back here and you have them synchronized again. So the PPS is something which can be really used for time synchronization. Okay, so that was about how what clock is good to use. It's always good to use a GNSS clock, right? Use UTC. The third problem is now how to synchronize multiple clocks. So we have now this problem where we have multiple PCs or microcontrollers or laptops or whatever, and we need to synchronize them somehow. And again, there are multiple options here. We start with option 1. We sync all of the clocks with GNSS, right? So what we could do, we could connect the GNSS receiver to all of those PCs or laptops or computing units. To each of them, we connect to a GNSS receiver and synchronize the internal operating system clock with the GNSS, with the PPS and the timestamps and time information coming from the receiver. That's possible. And then we have a synchronization between them, of course, indirectly in the order of below a microsecond. And this already would give us a synchronized network, let's say, right, of different sensors. So this is something that can be done. But what you have to do is you have to connect a receiver to each of the things, each of the PCs. Option 2 is synchronize the clocks via some clock synchronization protocol, right? There are two mainly, which there are even more, right? But there are two very famous one, which is called NTP, Network Time Protocol, and PTP, which is a precise time protocol. I don't want to really go into details of this and how this works. I just want to give an idea what's happening there, so you can basically, that you just get an idea. And without, this is not technically detailed and correct. It's just really on the surface and giving an idea of the thing. So let's start with a precise time protocol. The precise time protocol is working in a master slave mode, right? There's some master clock like this one here, right? And what we want to do is we assume that this is the clock. So it's coming here, you can see from the GPS, right? So this is, for example, synchronized with a GPS receiver clock. So it's the time which we want to have, and all the rest here are slaves. So what we want to synchronize these slave times with the master time here. And what we need to do here for the precise time protocol is, for example, if we have some switch in between or something, some hardware in that network, then this serves again here as a slave to the master, and at the same time as a master to the slaves which are connected. This is necessary because in the PTP, in the precise time protocol, all the measurements, the measurements, time measurements are necessary, are done in hardware, right? So the network hardware plays an important role here in this protocol. So what is this doing? There is some exchange of messages between master and slaves in order to synchronize the slaves, and I want to show how this roughly works. So here we have a master time. So this is a time evolving here when the arrow going down from the master clock, right? And this is our slave clock, right? So this is now going down here, and that's what we can see here is this is just numbers, right? So don't take this too serious, it's just an example. So here we have 100 seconds. The master time is at 100 seconds and the slave time is at 80 seconds. So we have some difference between the master and the slave time. And what happens here is there is some exchanging of packets in order to find out what the difference between those two clocks is, right? And what it usually is happening, there's a synchronization message sent from the master to the slave, right? And then the slave receives that information message. There is a follow-up message which contains the information and information about the exact time the first message has been sent, because it's not possible that the master measures the time of sending the message and writing it at the same time into that message, right? Because then there would be a delay. So we send a message, measure here when that was, and write it in a follow-up message. And then the receiver here receives that, and it receives also the information on when this has been sent, right? And what the slave can do then, it can correct, right? So it knows that there was 101 second, right, received, but it also knows that the own time was 83 seconds. So what it does, it adds those difference to the current timestamp, and now it has an updated timestamp. So it updates using the difference between that sending time and that reception time, and then it put that in updates the own slave clock. But this is still not the correct one, because this clock here, this time now, these 18 seconds here, does not include the actual travel time between master and slave, right? So this is not in there, and this is why there is a so-called delay request. So that means that the slave sends a request to the master, and the master then sends back the time when it received that delay request, right? So these 112 seconds here, when it receives that delay, are written into some reply, and the reply is then going here, right? And what then the master can do, the slave can do, it then can use this. It can use this 112 that it receives here, and can calculate the travel time between here and here. And because we have now two travel times, right? We went here, here, and here. We have to separate by 2, and can then again update the new slave clock here and write that here. So by sending a message here, or two messages actually, one back and then one back again, we can the slave is able to update the internal time so that it fits perfectly to the master time. And this is what's happening in this precise time protocol. One important thing here is that the measurement of the time is actually happening in hardware, right? So it's not going up to higher levels of the operating system, but the Ethernet card, the switches, and all the actual hardware which is needed or which is involved in this PTP protocol at the very low level of the network hardware, this is where the actual time measurement is happening. So it's avoiding all that things going up to the network stacks and to the operating system, all these things which may introduce additionally delays, which may depend on current processor loads and all these kind of things. And these are basically not included because the measurement of these time delays and the timestamp is done very close to the actual network hardware or in the network hardware, so that we avoid. So the PC, the operating system, doesn't even know about this, right? So this is just happening on the network hardware level, and this is why we can achieve very, very good accuracies in the order of microseconds or even smaller with this PTP protocol. But disadvantage, we need special hardware for that, right? Which may be expensive. The network time protocol, I also quickly want to mention what this is. We also have like a message, like delay message measurements, like I said before, right? One PC sending something to the other one, this is sending something back, and so on. And then there is some sort of estimation of time delays between PCs. This is usually not happening on the hardware, it's happening somewhere in the system. And because there are many of those delay measurements and some very fancy algorithms how to find out which are the best and which is good, and I don't want to go into details here about this, but there are many of these delay measurements involved, and some optimization algorithms then find out and estimate the best delay between each PC and some upper level of time accuracies. This is what we see here. We have here the best, so with the master clocks, right? This is usually called stratum 0, and then there are more of those. The next level is they are synchronized with these stratum 0 clocks, and then there's always a next level of or a lower level of accuracy, let's say, and each server here is synchronizing to some upper level clocks. As I said, I don't want to go into detail here. What I just want to mention that this is working very well in general, in the order of tens of milliseconds if it's over the network, over internet, and so on. And it can be even more accurate under certain conditions in local networks. But the main problem is that this is actually done for server networks which are running all the time, because these loops which are adjusting, like control loops which are adjusting the time information, they take some time to converge, right? So it's not that you switch something on and then it's synchronized straight away. It takes a while, and it's not really designed for sensors as we need it in our systems, right? It's good for server networks, and it's not so well designed for sensor networks or for sensor systems as we shown before. I still want to mention it here, but if you have the choice, use PTP, because this is designed for these systems. And there are even possibilities to do PTP without dedicated hardware. Of course, the accuracy is then not in the order of milliseconds, but yeah, it's still possible and potentially better for this type of applications than this network time protocol that I've shown here. Good. At the end, I want to give some examples how time synchronization is realized in systems that we used, and I can show you, of course, how this is done in our own mobile mapping system, which you have seen a few times already, which has this Zoller-Fröhlich profile scanner here, the IMU here, and also a GNSS receiver in here with the antenna on the top, right? So this is the system that we used for many of the examples that you've seen, and I just want to show you how time synchronization is done in here. So the inertial measurement unit, of course, is attached, has a GNSS receiver inside, which is attached to antenna, of course. And this means, as I mentioned in the very beginning of this course, of this lecture, that means that everything here in that IMU, so orientation, position, acceleration, angular rate, everything is already properly synchronized with UTC, because it is synchronized with the GNSS time and therefore with UTC. What it does additionally, it provides a PPS clock, and it also provides a message containing UTC time. This is the so-called GGA message in the NMEA protocol from GNSS receiver. So every GNSS receiver can provide these NMEA messages, and also this GDA message, which also contains position and some other things, but it also contains UTC time. And this profile scanner has an input for PPS and an input for this NMEA. So it is already prepared to receive PPS and time messages. And then what it does, it internally tags the data of the laser scanner already with the correct UTC time. Of course, it works also without this, right? But then the timestamps assigned to the laser scans, to the distance measurements, are not synchronized with a proper UTC or something. It's just an internal timestamp in this case. But if you have a PPS connected and it gets NMEA data, then the laser scanner tags every laser scan it does already with the correct time, right? And these are then written to a data file, right? So all the positions that are measured here with our scanner, right? All these positions are then written here into a data file, and every of those positions has a proper timestamp, UTC, right? And the positions here and the orientations and accelerations, everything that we get here, are also written to a data file, which is stored here on that machine, on that device, and it also contains a timestamp and then acceleration, x, y, z axis, and so on, right? All these data that coming from here. And then if this is just a kilohertz, and this is, or 100 hertz could be as well, right? And this is maybe a million hertz, a million hertz, then of course you still have to interpolate. So you still have to interpolate the positions. Like I said, this is a position data, and you have laser scan measurements in between. Then you have to somehow interpolate, of course, to always assign the correct position to the correct laser scanner, because the frequency of the sensor data is not the same, but at least the time base is the same, so we can do some proper interpolation. Okay, this is how this works in our mapping system, and I want to also show you another example, which I mentioned already in the beginning. So the idea that was a project that we did years ago already, and the idea was to control the placement of sugar beet seeds. And controlling this placement is not a new thing, and it was back then. It was also not a new thing, because you have these machines which place them equally distanced depending on the rotation of some wheel in here, right? So you have the seats here, and you drive along, and then it just tries to put equally distant sugar beets, right? What happens is, at the end, if you turn around and go back, then of course these they are not aligned anymore, right? Because the distance measurement which comes with this rotating wheel, of course, gets lost if you turn around at the end. That's one thing, right? So the idea was, what we want to put the sugar beet placed depending on the GNSS coordinate, and this is what was the idea. And I want to mention that here as an example, because time synchronization, of course, was very important here, because if the synchronization of this disk, which is rotating here with some control loop, which was controlled by a Kalman filter, wouldn't be synchronized properly with the GNSS measurement and all the other measurements, then of course this wouldn't work well. It used a real-time system, right? Control system. This is a real-time system, a real-time system from National Instruments, and it used sensors, GPS, angular rate sensor. This is all German. I'm sorry. Don't change that. This is an odometer. And this is GNSS, right? And then what I want to point out here is that the GNSS basically is synchronized using this NMEA message that I've showed before, and the PPS, similar to the laser scanner, used to synchronize this system here. And then on this system, there was a Kalman filter running using all these sensors to provide 1,000 Hertz position and orientation, and this is then used to control this wheel here in order to place the sugar beet in the correct position, right? So this was the rotation rate of this wheel was controlled and the phase as well, and then it was done in a way that the seed is placed exactly at the correct position. It was very important, of course, that everything was well synchronized. This is why I mentioned this here. Yeah. And this was the result. So we had 3 of those devices here, and this was some field where the tractor was driving. So this is always the position, right, of that seeding device here. And then what the colleagues did was a very stupid job, actually. They, after the seeds have been sown and the plants actually emerged, then they went here with a very high precision total station, geodetic total station system, which is an accuracy of about 1 centimeter or even less. And they measured all of the sugar beets plants. And this was then the distance of the emerged sugar beet plant to the actual position that it was planned to be. So we had an accuracy in the order of 2 centimeters on our controlled placement of the sugar beet. And this was actually pretty good because the GNSS accuracy is in the similar order, right? And it also includes the fact that the plant is, I know if you look from the side, right, and you place a sugar beet here, then, then it's still possible that it's not staying here, it's rolling to here, right? And then the plant grows, and it grows like this, right? So there is some uncertainty in placement of the sugar bean and where the plant is actually done, which also is in the order of centimeters. So we can estimate that the component due to time synchronization errors is basically 0, right? Because what's left over here is due to GPS and due to other things which happen in this procedure. Okay, so to summarize, what have you learned today? So you learned today that time synchronization between sensors is important, and why is it important, right? That's a very important thing. So you need to understand why this is important, and also good to know what is the synchronization accuracy that is needed. Of course, that depends on your accuracy, right? If you drive a system through the city, which where you find with like 20-30 centimeters accuracy, because maybe your laser scanner is anyway not so accurate, then it might be totally fine to go with 10 milliseconds accuracy. But if you go towards the centimeter accuracy, then you have to really look for below millimeters. What are critical points in synchronization? I try to explain. So what do you actually have to care for? Why is it difficult to do it? What GNSS receivers can help you for synchronization, because this is a very, very helpful thing to have a GNSS receiver, because it gives you a really good clock. And some words on how clocks in computer networks can be synchronized. This was just a very rough overview, so it's possible to make extra lectures on this, but yeah, this is not the goal of this here. And yeah, I also gave an example how sender synchronization is realized in our own mapping system. With this, I want to thank you and see you next time.